Start. So good morning, everyone. So as you know, my name is Roshan. So currently I'm a postdoctoral research fellow at Australian Robotics Center. So thank you very much for joining today's sessions. So today we are going to explore one of the most exciting transformations in modern manufacturing, which is how robotics is shaping the future of welding. As we move into an era of advanced manufacturing, welding remains one of the most critical process across industries from automotive, aerospace to construction, and even shipbuilding as well. However, welding is undergoing a major transformation, so driven by multiple factors. In this presentation, I will just go through some of the key things, which includes the growing demands for welding automations and why robotic solutions are needed now more than ever, and some of the latest advancement in robotic welding technologies, some of the key insights from my ongoing literature review, systematic literature review that I've been doing. So in short, this session will highlight how human expertise and robotic intelligence can work together to create more efficient, safe, and high quality welding processes. So before we dive into the robotic welding, let's give you a quick overview of the fundamentals. So what exactly is welding and why it is very important. So at its core, welding is a process that joins materials, typically metals, by melting and fusing them together. So it is one of the most essential fabrication techniques forming the backbone of industries such as automotive, aerospace, constructions as well. Whether it's the frame of a car or the structural framework of a high-rising building, welding is what it holds together. So over the years, welding technology has evolved significantly, and today we use several different welding processes, each suited for specific application. I'll briefly go through some of them. The first one is the arc welding. So this includes MIG and stick welding, where an electric arc generates intense heats to melt and join metals. So arc welding is widely used due to its versatility, speed, and ability to produce strong welds. And the second one is gas welding. It uses a gas flame, typically oxygen and acetylene, to generate heat and melt the metal. While less common in industry settings today, it's still used for repair work and some specialized applications as well. The third one is called resistant welding. Instead of an external heat source, this method uses electrical resistance to generate heat between metal surfaces. So it's commonly used in automotive manufacturing and thin sheet welding applications as well. The other one is laser welding. So it's a high precision welding technique and mainly used in aerospace and medical device manufacturing sectors where the precision is critical. The other one is called friction stir welding. Unlike conventional welding, this is a solid state process, meaning the metal does not melt. Instead, a rotating tool stirs and joins the materials together, making it ideal for like lightweight materials like aluminum. And it's also often used in aerospace and transportation industries. So each of these methods has its own strengths and applications. But currently, there is a growing demand for welding compared to past. So several global trends are driving these needs. So one of the trends is an infrastructure boom. So government and industries worldwide are investing heavily in large-scale infrastructure projects, including transport, energy, and construction. For example, in Australia, transportation engineering constructions expenditure has reached record levels. So approximately 45 Australian dollars, which is nearly 30% higher than the pre-boom levels, has been invested. So this means more bridges, railways, smart highways, and renewable energy installation. So all of which requires extensive welding. So at every stage, so from construction and also for maintenance as well. And the second reason is the rapid expansion of some emerging sectors. So the rise of electrical vehicles, renewable energy systems, and high-tech manufacturing, especially in aerospace, robotics, and automotive, is creating demands for welding. For example, solar panel production and turbine assembly and battery manufacturing also rely heavily on welding as well. And one of the other and another important reason there's a sudden demand is because of global supply chain diversification. So in recent years, global disruptions such as COVID-19 pandemic, geopolitical tensions, and material shortages have pushed the manufacturers to onshore or nearshore their production, to reduce their dependencies on foreign suppliers. 2021 survey, which was held a few years ago, revealed that during that time, 55% of Australian manufacturers wanted to reshore their operations by 2023. So all of these factors contributed to an increasing demand for welding. And as the demand for the welding increases, the welding industry is confronted with some new challenges as well. First, the rise of advanced materials like lightweight alloys and composite, which are used in some of the emerging sectors, demanded for some unprecedented levels of precision and consistency in weld quality. So traditional welding methods often struggle with consistency when dealing with thin materials, complex geometries, leading to defects and inefficiencies. The second challenge is the shortage of skilled welders. So as per a survey conducted by Weld Australia in 2024, only 16% of welding workshops in Australia are operating at full capacity, and 25% of them cite a lack of skilled workers as their biggest challenge. Also, looking ahead, Australia is projected to have a deficit of 70,000 welders by 2030. So this shortage leads to production delays, increased cost, and a growing gap between industry demand and available workforce. And the third challenge is the need for faster production and efficiency. So high volume industries like electrical vehicles, shipbuildings, and constructions require welding processes that are not only precise, but also much faster than before as well. So scaling up production while maintaining quality and efficiency is becoming a more challenge, as traditional welding methods struggles to keep up with the increasing market demand. So in an industries where production speed directly impacts competitiveness, finding ways to increase output without compromising the weld quality is becoming a top priority now. To overcome these obstacles, companies are turning towards automation. Why? Because automation helps to enhance welding capabilities, making process more consistent, scalable, and adaptable to modern manufacturing needs. There are multiple automation approaches that are currently used, and each of them have their pros and cons. The first one is a fixed automation method. So this includes a dedicated high-speed welding system, which is designed for mass production. This fixed automation is extremely fast and precise, making it ideal for high-volume, repetitive tasks. However, it lacks flexibility. Once it is set up for a specific application, it can't easily adapt to a new design or product variations. And the second type of automation is a CNC welding machines-based automation. So these systems offer high precision and repeatability, making them ideal for industries requiring tight tolerance and complex welding geometries. However, their flexibility is limited. So while they are flexible to a certain degree, they can't reach beyond a certain position or orientations, which still require a manual setup. And also it is limited by its workbench. And the next automation approach is the additive manufacturing. This is one of the most flexible and adaptable manufacturing methods, capable of creating complex metal structures layer by layer. But the issue is speed and productivity remain a major limitation. So metal 3D printing is far slower than the traditional welding techniques and is not yet practical for large-scale welding applications. So it leads us to the last option, which is the robotic welding. Unlike fixed automation, robots can be programmed to handle different welding tasks. Compared to CNC systems, they offer greater adaptability for different joint types and materials. And also, unlike additive manufacturing, robotic welding is highly productive, making it ideal for both mass production and custom fabrication as well. So as industry demands great efficiency, adaptability, and precision, robotic welding is emerging as the most effective and scalable solution. And if you look at the generic definition of what robotic welding is, it's simply put, robotic welding is the automated process of using programmable robotic arms to perform welding tasks. But robotic welding is in fact not new. The first welding robot using inmate was introduced in 1962. Since then, robotic welding have evolved dramatically, incorporating advanced sensors, AI-driven process control, and adaptive capabilities to handle a wide range of materials and applications. And today, due to high demand, more companies are investing in welding robots than ever before. As per one of the survey in 2023, the robotic welding market was 8.63 billion USD dollars, and it is expected to almost triple in 2034. And based on how welding robots are deployed and interact with the environment, the robotic welding can be classified into three major categories. They are mobile welding robots, industrial welding robots, and collaborative welding robots. So we'll quickly have an overview of these different types of robot. The first one is mobile welding robot. So what exactly mobile welding robot is, it's unlike stationary welding robots. These are autonomous or semi-autonomous systems that can move freely within a workspace to perform welding tasks. Some of the key features of mobile welding robots are, the first one is it has multi-axis flexibility. So unlike traditional robots that are just fixed in one place, mobile welding robots can operate in multiple orientations, making them ideal for like more complex and large-scale structures where welds are required in difficult areas to reach. And the second feature of the mobile welding robots is the ability to operate them remotely or teleoperate them as well. So many welding robots can be supervised or adjusted remotely, so allowing the operators to intervene, adjust welding parameters, or even control the robot from a distance. So this is specifically valuable in hazardous or hard to access environments as well. Because of their ability to move around in different work sites, these robots are particularly useful in constructions and infrastructure, where there is large-scale structures, bridges, and pipelines, which often require welding in like restricted locations. And the second and most applied area is shipbuilding and marine engineering. So the complexity and the scale of shipbuilding demands some flexibility similar to the mobile welding robots. And if you look at the second category, the industrial welding robots, in contrast to the mobile welding robots, these robots are designed for high speed and high precision automation in mass production environments. So these robots are typically fixed in welding cells, and it has their own unique features as well. So one of it is high speed and high precision. So these robots operate much faster than the manual welding, achieve sub-millimeter accuracy, which is very critical in industries that require tight tolerance and more high repeatability as well. Also, the ability to integrate advanced sensor is one of the key features. And also these robots can handle high payload and stiffness. So these robots are built to handle large and heavy components. So while maintaining the rigidity and stability, ensuring consistent performance even under heavy workloads or heavy pressure environments. So some of the applications of this industrial welding robot includes automations, automotive manufacturing. So the automotive industry was one of the first that adopted industrial welding robots. So these robots are at the moment responsible for welding car frames, chassis components, and structural reinforcements. And also it is widely used in aerospace and defense as well. So the aerospace and defense industries require extreme precision in welding because of high performance requirements of aircraft and military equipment. So industrial welding robots help to ensure the consistent and also defect-free welds that meet strict safety and quality standards set by these aerospace and defense industry. The third type of robot is collaborative welding robots. So as we see, industrial welding robots are designed for mass production, but if you want the robot to work safely alongside human welders, that's where actually the collaborative welding robots come in. So collaborative robots, or commonly known as cobots, which are used for welding, are specifically designed to work alongside human welders in shared workspaces. So unlike traditional industrial robots, which require cages and strict separation from human workers, cobots are equipped with built-in features, which allows them to operate safely and efficiently alongside people. Some of the key features of these collaborative welding robots include the quick setup. So cobots are designed to be plug and play, so meaning they are very easy to install and deploy without extensive safety requirements, and also they are compact and mobile design. So unlike large industrial robots that require fixed workstations, cobot can be mounted on a welding table or a mobile cart. And some of the applications of collaborative welding robots includes manufacturing. Many small to medium-sized manufacturers are turning to cobots. At the same time, they are used in aerospace and defense as well, where they have to share the workspace with co-workers. And when considering robot welding, one of the most common questions that comes up is, should we use an industrial welding robot or a collaborative welding cobot? There's often a confusion which type of robot is the best fit. But the reality is both the industrial and collaborative robots have their own advantages, and the right choice depends on the specific needs of these applications. So let's break down by comparing the key differences. So if you want to work with human, industrial welding robots are designed for full automations, like with little to no human interaction. So that's not an option. But if you want to work with cobots, are the ones that can handle humans because they're designed to work safely alongside human workers. So they come in with like built-in force sensors and collision sensors that allows them to detect and respond to human presence. So if you want to share a workspace, cobot is the best option. But on the other hand, if you look at the precision and consistency, industrial robots offer extremely high precision, often achieving sub-millimeter accuracy. So this makes them ideal for application requiring absolute consistency and repeatability. On the other hand, cobots are slightly lower than the industrial robots due to their focus on safety and collaboration rather than precision. For an example, if you compare two similar robots from an industrial and collaborative perspective, Farnuk Archmate 100ID is an industrial robot, and UR10E is a collaborative robot. Both of them have a similar payload. But the repeatability of Archmate is plus or minus 0.02 millimeter. But on the other hand, UR10E has a bit low repeatability, which is 0.05 millimeter. So if precision is more valued, then it's better to go with industrial robot. But if you have to share the workspace at the same time with some decent precision, then cobot is a good option. Likewise, if you look at the speed and productivity, industrial robots operate at high speeds. Cobots operates at a more moderate speed because as they designed to prioritize safety over raw productivity. So the speed of Archmate, for example, is almost 4 times the speed of UR10E if you look at the maximum joint speed of both the robots. And also, if you look at the safety requirements, so industrial robots require external safety measures. Cobots are, as I mentioned, equipped with built-in safety features. So there's eliminating the need for cages that are required for industrial robots. And also in view of setup and deployment time, industrial robots require weeks or even months for setup because we have to build up the whole cage that is required for the installation. But if you look at the cobots, as I mentioned, it's like plug and play. So it's very fast setup time, often within a few hours. And also, if you look at the programming perspective, industrial robots require a bit of high-level programming. And also, they often use offline simulation tools to define complex welding paths before deployment. But if you look at the cobots programming, which is shown in the picture down, so they normally use kind of a blockly approach in the sense we can just drag and drop interfaces, and with manual teaching methods and intuitive controls, we can even non-experts will be able to easily control or program the collaborative robots. So in short, industrial welding robots are more ideal for high value, high precision, and fully automated welding in mass production environments like automotive and aerospace. And collaborative welding robots are best for flexible, small batch production and human-robot collaboration and businesses needing easy-to-use, adaptable welding automations. So always the choice depends on the application perspective. And as industries push for greater automations, robotics welding is evolving beyond just automation as well. So several key technologies are shaping the future of robotic welding and welding in general as well. So making it more smarter and more reliable and easy to implement as well. So first of its kind is AI and data analytics, which is becoming more indispensable in quality assurance, allowing robotic systems to automatically detect defects and even predict failures when it might occur. So neural networks, for instance, can classify defects in real time, greatly reducing the downtime and enabling proactive maintenance strategies. So the second is robots are being used for advanced welding training and education approaches as well. So to address the skill gap in welding, advanced training and educational approaches are also taking center stage. So robotic welding systems are now being integrated into training programs, allowing the students and trainees to gain hands-on experience with automatic welding processes without any safety issues or without any material wastage. And one of the most exciting advancement in robotic welding is the development of adaptive welding systems. So unlike traditional welding robots that just follow pre-programmed path, similar to how manual welders change their parameters while welding, adaptive robotic welding uses real-time sensor feedback as well from vision systems, laser scanners, and force scanners, and they dynamically adjust the welding parameters. So this approach allows the robot to dynamically adjust parameters and optimize the welding as well. So the question comes, why does the adaptive welding stands out? Is because while AI-based quality assurance can identify defects after welding is complete, the product may be already wasted, which can be costly, especially for high value or limited materials. So adaptive robotic welding goes on one step further by actively preventing defects before they occur. So by optimizing parameters in real time, it improves weld quality, reduces the material waste, and enhances overall efficiency as well, making it a game changer in robotic welding. So currently, as part of a research into adaptive robotic welding, we are conducting a systematic literature review to analyze the latest advancement trends and challenges in this field. So the goal of this review is to identify some of the key innovations, evaluate the gaps in existing research, and also to determine the direction of future developments in adaptive robotic welding. So to ensure a comprehensive review, we have used multiple academic databases, which include Scopus, Web of Science, and IEEE Explorer as well. So when we designed the search string, we captured the most relevant studies, and the search string used terms which are similar to adaptive welding, and also which includes robotic welding as well. All these terms we identified based on our initial background study. So using this approach, we retrieved around 3,055 relevant publications. So after removing the duplicates, and we are now in the process of completing the review. So in this presentation, I would just like to highlight some of the initial findings that we found from this systematic literature review. One of the critical challenge in robotic welding is ensuring that the welding torch remain precisely aligned with the seam throughout the whole process. So traditional robotic welding follows like fixed pre-programmed paths, but this approach has major limitation. It does not adapt when workpiece shifts due to some external effects such as thermal expansion, fit-up errors, or material inconsistencies. So sensor-based seam tracking solved this problem by allowing the real-time adjustment. So instead of following a rigid path, the welding system continuously monitors the weld joint and make corrections on the move. So this ensures that the torch stays aligned and also reduces the defects and improves the weld quality, even when there are variations in the workspace. So several sensing technologies are discussed in the literature to enable this real-time tracking and adaptive control. So some of them include vision or camera-based seam tracking, which uses optical sensors and image processing to detect and track the weld seam in real time. And the another approach is based on arc sensor seam tracking. So it monitors a welding arc voltage and current fluctuation to infer seam position. The another approach is based on laser seam tracking. It uses laser triangulation or structured laser light to precisely map the weld joint. And one of the unique approach includes a fixture-based method as well. So it integrates force or additional sensors directly into the welding fixtures to detect part deviation and misalignment and to optimize the weld path as well. Besides this technology, another major advancement in adaptive robotic welding is real-time parameter adaptation. So parameter in the sense the parameter which completely define the welding. So unlike traditional robotic welding system that uses like fixed welding parameters throughout the process, real-time adaptation allow the systems to dynamically adjust key welding variables such as wire feed speed, welding current, and travel speed. So some of the key technologies proposed in the literature related to this real-time parameter adaptation include wire feed speed, and welding current adjustment. So adjusting the wire speed and welding current in real time helps to maintain stable arc and compensate for material inconsistencies as well. So another approach is welding weld penetration control. So it simulates a human welder response model to enable the robot to adjust welding current dynamically, ensuring consistent penetration under varying conditions as well. So third approach is hybrid or laser arc adjustment. So hybrid welding techniques like laser-assisted arc welding allow automatic adaptation of robot speed and arc setting based on joint gaps as well. So these are some of the key technologies that are proposed and are currently researched in adaptive robotic welding that we found from our initial analysis. Despite all these advancements in adaptive robotic welding, there are still several technical and practical challenges that need to be addressed before it can be fully integrated into industrial settings. So one of them is the environmental factors affecting the sensor performance. So sensor plays a crucial role in adaptive weldings, but the effectiveness can be compromised by arc light reflections, fumes, and harsh environmental conditions as well. So vision-based sim tracking, for instance, struggles in high glare conditions, requiring advanced filterings or sensor fusion techniques to improve accuracy. And another major challenge is the legacy welding systems that are currently used in manufacturing industries. So many industrial welding facilities still rely on older non-adaptive robotic systems, which were not designed for like AI-driven welding control. And another challenge is the thermal distortion and residual stress that affects the weld path accuracy. So heat input from welding causes some thermal expansion and contraction as well, which can alter the weld path in real time. So even with the sensor-based tracking, compensating for thermal warping and stress buildups remains a big challenge. And another challenge is multi-sensor data fusion. So SIM tracking systems rely on multiple inputs, vision arc voltage, like laser scans and force sensors, but processing these diverse data stream in real time without much of lagging or conflicts remains a bit of a challenge as well. And another challenge is highly reflective metals like aluminum and titanium, which complicate the vision and laser sensing. So shiny materials like aluminum and titanium reflect light, so it disrupts the vision-based tracking systems. So specialized sensor coatings like polarized optical filters or hybrid sensing approaches are needed to overcome these limitations. So as research in adaptive robotic welding and sensor fusion advances, so solution to these challenges will continue to emerge in the future. And so before I just wrap it up, I just want to put this out there. So at Swinburne University, we have an advanced collaborative robotic welding setup, which is located in the Intelligence Robotic Lab. So if anyone is interested in exploring robotic welding projects, whether it's solving a specific industry challenge or testing new welding automation approaches or partnering on research initiatives, we would love to connect and collaborate. So for any inquiries or project discussions, please reach out to our lab director, Professor Matt Isaacson, through the email. And with that, I conclude my presentation. And once again, thank you all for joining today and for your time. So if you have any question, feel free to unmute and ask.
Yeah, really great presentation, Roshan.
Thanks. Thank you, Fred. Yeah.
Yeah, so I think you gave a really nice overview of all the sort of like different technologies out there and some of the more like technical kind of challenges.
Yeah.
I was interested, like, on your opinion on because I mean, cobots aren't really widely used yet in sort of welding industry, right?
Yep.
So do you think that's because of these kind of like more kind of like micro scale like technical challenges, or do you think there's some like kind of broader gap there?
So one of the main I had some interaction with some of the welders when we had the Weld Australia show. So one of the biggest concern they put forward was the initial investment cost. Since it's a new technologies, most of the welding companies are SMEs, so they are a bit reluctant to just to put a step forward and go ahead with that investment. But some of the integrators, they are coming up with the demos and they are trying to show them what they can actually work on it and trying to implement it. So they are trying their best to go ahead with that approach. But compared to industrial robots, cobots are more appealing for them. The main reason is because they can do welding parallelly with the cobot. So you don't have to just let it run, because most of the time, welders, even though it's run automatically, they wanted to see what is happening when welding, whether it's good or not with their eye. So when you have that shared workspace approach, it's becoming more appealing compared to the industrial robots. But initial investment cost, more than the technology, the initial investment cost is one of the things that becomes more challenging. But when I showed a demo of how the robot can be used to weld it, even though I have zero experience in welding previously, they were a bit surprised, and it becomes kind of a persuasive for them as well. So because they know that when you want to do a manual welding, it takes a long time of practice and experience as well. So people are moving towards that one, but I think we have to do more of kind of an education approach to introduce cobot welding approaches to the industry people. Yeah.
That's interesting. Yeah, thanks. I have one more quick question, if you don't mind.
Sure.
So you have the graph of the expected kind of industry size of the cobot welding,
Yep.
robot welding. I'm not sure if you can pull up that graph, but it looked like in like 2034, you're expecting it to like kind of triple. That to me, that seems like kind of, I would expect, like if you kind of look at the general kind of robotics industry
Yep.
trends, you would expect that sort of increase within the next kind of like few years, as opposed to kind of like 10-year scale. So is that something like specific to welding, or I'm not sure if you kind of looked into this?
Yes, I had a look actually. So it kind of both, as you mentioned. So for example, one of the reasons I mentioned is emerging technologies like EVs and then solar panel manufacturing requires both robots for assembling at the same time for welding as well. So it has kind of it impacts both robots as a complete field at the same time welding as well. But one of the key things, especially in Australia, is the shortage of welders. So that kind of pushes more towards automations. And as I mentioned, when it comes to automation, robotic welding look more appealing. So those are kind of, it's a mix of both reasons. So like generic approach towards robotics at the same time, specifically for welding as well. But having almost triple the market in 10 years is quite an impressive, like a sudden surge in, especially when it comes to robotic welding. Yeah.
Yeah, I'll let other people ask questions. Thanks.
Yeah, so I have a comment too. First of all, like really interesting, a lot of new things for me. So thank you very much. I like this, the study to systematic review is always really good to, get the background and identify the gaps. I was having one comment regarding the sort of comparison of industrial robots versus cobots. So first of all, if you look at sort of the ISO 10218, the focus really is, and it's going to be even stronger, the focus is on collaborative application, not as much as collaborative robots. And if you look at the 4 defined collaborative applications, one of them is lead teach, right? So that is in parallel to sort of force and power limited robots. And even an industrial robot can do lead teach. So, and for welding, the typical part, you don't want someone there when you're welding. You want to be there before the welding starts. And that also, many industrial robots can already do that. So you don't need a cobot for that purpose specifically. The second thing is in general, one problem with robotic welding is that in order to do like arc welding, the one problem is, as we saw in many of these videos, that is to reach around, to reach everywhere on the weld. And the cobots are typically small with small reach. And so you would need, a positioner, or you might put a robot on a track. But then there are no collaborative robot systems that are certified collaborative, combining external axis and the robot itself. And that is where there's definitely room for improvement, right? Because the robots they're speed limited, so collision is okay, but then you put it on a track, clearly you can achieve larger speed. And then they would have to sort of be a certificate for that. Maybe the robot speed itself has to be reduced and similar things. And the positioner may not be safe to be close to it either, right? So that's just 2 comments regarding collaborative versus industrial robots for welding. But thank you very much for the presentation.
Thanks, man. Thanks for pointing it out. Actually, I just wanted to highlight that one as well, because yesterday I was having a conversation with one of the robot welding integrators. So one of the things they actually highlighted is they wanted to integrate a cobot on a linear track, but as Matt's highlighted, the cobot is actually collaborative, but the linear track is not. So they have to have redefined all those safety parameters to adhere to that one. And there are companies which are looking into that one, but still you need external sensors to make it more compliance. But the kind of off-the-shelf solution is still not there for those type of small things here.
Just a comment about that, actually. So having like a static base with even with like a welder on the end effector, does that adhere to like safety standard? Like, can you have someone in a shared workspace with a robot and a welding tool?
The welding tool, actually, even if you just if you take the welding torch and touch it, it's not going to start welding unless otherwise it completes the loop, for an example, in arc welding. So unless it just comes out, if you just break the tool, the torch from the robot, it's very unlikely to cause damage to the person when it comes to the robot. But as they always say, for cobot, a safety analysis need to be carried out, defining this, limiting the speed and other features as well, maybe the workspace as well. So when you have a bench, you can actually limit the workspace and also the speed and the sensitivity of the robot. So those parameters need to be fine-tuned as well when it comes to the implementation. Yeah.
But like currently, can a cobot and a person actually do welding together at the same time in like a shared workspace, or is that safety?
I mean, if you implement the proper, if you carry out proper safety analysis, I think definitely yes. Because even in one of the video I have showed, you can see, I don't know where it is. You can see a person working together with the. Yeah. So you can see on the side the robot is welding, and on the other side the person is doing his other welding on other complex structures. So there are applications where you can, as the cobot defined, you can share the workspace here.
Great talk, thank you. Got a question regarding the AI elements of robotic welding and the weld path forming, because if you've got everything fixed, it's easy to determine what the weld path is. But if the robot's moving or the item to be welded is moving, is a lot of work done in the AI path planning for robot welding?
Already they have some integrated features in the system, welding system, that, for an example, you can use a laser linear line scan and integrate it, and then based on that feedback, you can just train a model. Mainly that deviation comes in very millimeter size, because it does, if you have a strong fixtures, normally it moves maybe because in millimeter by millimeter, or maybe because of thermal expansion. So people are proposing some models which can predict the movement depending on how far it is deviating at the initial standard. But in view of AI integrations, they don't have anything which is already integrated, but they have kind of a normal non-AI systems that actually can use a line scan to track the seam path when they're doing the welding. Yeah.
Okay, thank you.
So any other questions or?